Thank you, Ramon, for a very nice introduction, and I'm very happy to be here. And I'm glad you guys have stuck around until the last day here. But this is a really interesting topic, and I actually think if you've learned anything this week, probably the stuff you learned on the first day and the stuff you're going to learn today are the most useful. So, all right. So basically, what we're going to do today is talk about general techniques for modeling sequential data with neural networks. The standard architecture for doing this is something called a recurrent neural network model. This is a name for a broad class of models that consist of a whole bunch of different specific instantiations, and we're going to talk throughout this about a variety of different applications. So in part one, we're going to go over language modeling as kind of our motivating application. That's just saying, what does language look like? We're going to build a neural network that tells us basically what the next word is given a prefix and builds and represents a distribution over all the possible sentences that one might want to say. And these are really good models for doing this. This is going to be used to analyze some of the challenges that we face when modeling sequential data. So you can think of, the big one is going to be when we make a decision later in a sequence, the information that tells us that we need to make a particular decision may have occurred quite some time back far in the past relative to sort of how time progresses in the sequence. And establishing that connection and letting the learner discover that there's this correlation spread across time is really sort of the key thing that motivates innovations in recurrent neural networks. And so we're going to talk about sort of what the problem is and how people have solved it. In part two, we're going to talk about conditioning on sequences and generating sequences conditional on other things. And this is a really useful application. A whole bunch of problems in artificial intelligence can be viewed as conditioning on a sequence of inputs and generating a sequence of outputs. There are a couple of standard techniques that have been very influential for solving this problem, namely attention. And then, time permitting, I've got kind of a lot of material I want to get through. We'll talk about some implementation tricks that you can use to improve performance and get a lot out of your computational resources. So the way I'm going to start this off this morning is by talking about neural networks as feature inducers. So I didn't hear Biksha's talk yesterday morning, but I expect he would have presented this view of neural networks as one way of looking at them as things that discover their own features. So a traditional idea is in machine learning, what you saw in the first couple of days, is an engineer designs the features that they think are going to be predictive for the task at hand. So imagine you're doing something like linear regression. You want to predict a continuous valued vector, and you have some features that you think are predictive of that. And you assume further that there's a linear relationship. So basically, we've got this functional form. So x's represent our input vectors of features. W is this matrix, and W is a parameter matrix, and B is a bias vector. And then we optimize this loss function, and we can do this by gradient descent, or we can solve for the minimal solution analytically because the functional form is so conveniently simple. Now the trick here is these x's, they have to be designed carefully. They have to be in a linear relationship to the things that you're predicting. Otherwise, yeah, you're going to minimize this, but it might not be a very good model. It might not generalize to the test data you've got. In fact, it might not even fit the training data that you've got very well. So we can think about a nonlinear extension to linear regression as follows. Rather than using the features that we might easily be able to measure x directly in the linear regression, we're instead going to compute this vector h just again by passing it through this linear layer, this matrix vector product plus a bias, and then we're going to pass this through a nonlinearity, which I've just designated as G here. And of course, you guys have seen plenty of this week. So that'll be tan H or a rel U or whatever. One of the interesting early results, one of the few theoretical successes we've had, is actually showing it doesn't much matter in the limit what nonlinearity you use there. As long as that function is nonlinear, eventually the learner will be able to, and given enough capacity in H, you can learn any function with any nonlinearity. Now in practice, some of them are a little bit easier to optimize than others, so we use things like the hyperbolic tangent. So that's just a little bit of theoretical background there. And then this H is going to become the features in our linear regression. So I put these two arrows to point that really the output of this model in linear regression and in nonlinear regression is still just a linear layer. So at the final part, you're doing the exact same thing. And the loss function is going to be exactly the same. Now, the nice thing about this is, of course, we can use naive features, X, that are easy to measure, and compute this hidden activation that'll then let them go on and stand in a linear relationship to the things that you're trying to predict. So what functions can this compute, actually? And so if H becomes big enough, that is, if it has enough dimensions, and you get to pick the number of dimensions, it can represent any vector-valued function to any degree of precision. So if you want to fit your data better and it's not fitting so well, you just need to add dimensions and keep optimizing longer, and eventually you're going to get there. Now, that doesn't mean it's going to generalize well. You do run the risk of overfitting, but this is a very, very powerful function, obviously, and it's much more powerful than linear regression, which can only represent, obviously, linear functions. So the way I want you to think about this going forward in this lecture is H is a set of induced features in what's otherwise just a linear classifier. And in some sense, the network here, that first line, is doing the job of a feature engineer. And so we're going to be going into domains, namely sequences, where I think it's actually quite hard to engineer features very well. I'm not going to say, I used to spend a lot of time doing manual feature engineering, and especially when you're working with domain experts, feature engineers, or domain experts, know a lot about what features are likely to be useful. And we shouldn't lose sight of the fact that that was a good way to make our models a little bit smarter by building in a little bit of human intelligence. But there are domains, in particular sequences, where we're tasked with representing something that we don't always have the best intuitions. And that's really where neural networks, I think, are particularly exciting. Okay, so recurrent neural networks. So first I'm going to just say lots of interesting data, sequential in nature. We focused a lot this week on language, but so we can think of course, words of words and sentences as a sequence. We could think of DNA as a sequence. We can think of notes in a melody. Maybe we want to generate music as a sequence. We can think of stock market returns as a sequence. All of this stuff is sequential. You know, a lot of people, my company that I work at now is very interested in behaving sensibly, learning to build agents that can solve tasks. You can think about the history of your experience in an environment as a sequence. You can think of the history of things you did this morning as a sequence. And all of those things can be modeled, and we can make decisions about, given that past, what should we do in the future. So this is a very, very powerful idea. And the big question that we often, one of the big questions we face when modeling sequences is how do we represent an arbitrarily long history? So in general, what we're going to be thinking about today is, given a history of actions, what do I do next? And since sequences can be unbounded in length, this becomes a hard problem. But what we're going to use is the technique we just saw, where we're going to let a network decide what the features are, and that's going to be the representation that we use. So here's the nonlinear regression we started with, also called feed-forward neural network. You guys, I hope, are very comfortable with this You worked with them yesterday in the lab, and Biksha told you all about them yesterday morning. The innovation that we're going to use to turn this from a feed-forward neural network into a recurrent neural network is quite simple. So remember, right now we've got this input x that we're using to compute this hidden vector. Now we're going to think about a sequence of inputs, x sub t. And what we're going to do is we're going to then define a corresponding sequence of hidden activations, h sub t. And this h sub t is going to look very much like the hidden activation for a feed-forward neural network, except there are going to be two inputs. There's going to be the input x sub t at the current time step, but there's also going to be the previous hidden state that we computed, h sub t minus 1. So we can, and we're going to, both of these are going to have a matrix associated with them. And in fact, we can rewrite this in a slightly more convenient form, where it really becomes clear that we're just computing the same kind of function, just with this more complex or more interesting input representation. So this notation I'm using here with this bracket with this semicolon in it, that just means take those two vectors and concatenate them. So we've got a vector representing our current inputs. We've got a vector representing our previous hidden activations. We're going to concatenate those two together, and that is going to be the thing, the naive features that we extract a new representation from, using this simple nonlinear form there. And then we're going to, say, make a prediction at every time step, or we'll just compute this HT. So we've got, the new innovation is we've got this hidden dependency at every time step on the previous hidden state. So what does this mean, though, for computing this value? We've got this funny loop here. So when we actually work with these things, we're going to unroll this in time. So we're going to start with something, say x1, feed it into this hidden, compute this first hidden unit, and then we're going to also, though, have to define an initial condition, h0. And often we just set this to be a vector of zeros. But you can actually treat that as a free parameter that can be optimized. This, generally adding parameters to models is useful. You fit the data a little bit better. It depends, again, on if you're in a regime where you've got sort of more data than you need to learn the function or not enough, whether that's going to win. So we do define this sort of initial base case for this. And then we just repeat this process. And so as we unroll over time, we end up with something that doesn't have these loops. And so finally, we're going to at some point reach the last element in our sequence. And that's going to be determined by the data itself. So you don't have to worry in the same way you did with hidden Markov models that, for example, Noah talked about on Friday, about stopping probabilities or anything like that. Now later we're going to come back and talk about turning recurrent neural networks into language models, and there will be things like stopping probabilities into those. But in general, for now, we're just going to assume we know what the sequence length is, and we want to model some relationship between a sequence and some prediction conditional on the sequence. So how do we train the recurrent neural networks parameters? Well, let's assume, for the sake of argument, that at every time step, we're going to be making some prediction. And that prediction is going to be, for example, a summary of not just what's going on at the current time step, but there's going to potentially be a dependence on the previous time step. So maybe we're doing weather forecasting, and every day our XTs are measurements of barometric pressure and humidity and all these things that meteorologists look at. And so we're going to look at those, and we're going to forecast. Is it going to rain or snow or have wildfires? This is it's useful to look at the current information, the current statistics when making that decision, but it's probably also useful to know, are things changing rapidly? So you don't want to just have information about today's barometric pressure. You want to know, are things going down, for example? That might be indicative that a storm is moving in or something like that. And so we want to have this. So our inputs are going to be these measurements, and our outputs are going to be some, say, regression over the kinds of weather events we might see. And the way we're going to train this is we're going to assume that we have some historical data where we know what actually happened. So did it rain, did it snow? And we're going to compare those two things, and we're going to compute some cost function. And this cost function can be whatever you like. It can be a squared error, it can be a cross entropy, it can be any other sort of cost, where it doesn't matter for our purposes. But we're going to have this prediction, this y hat one, and then the true value y1, and those are going to come together to be a cost. So we're going to do this for all of these things at all time steps for our historical data. And each of these costs we're going to aggregate together to compute a final cost, which I've called script f here. And the idea is that this unrolled computation graph, this is a computation graph. You can think about each of these arrows representing these matrix vector products followed by nonlinearities, and we can then compute derivatives with respect to the values in each of these cells with respect to the incoming arrows, and we can use the chain rule then to find the derivative with respect to some distant cell with respect to some other distant cell. So let's look at what this. Let's look at this idea. So basically, we're going to look at f, and we're going to say this aggregates a big error. And what we want to do is minimize it. So we want to know the derivative with respect to f of all the things that are contributing to that error. And so we can think about f as sending back little error messages along its incoming edges. So that's what these little dashed red arrows are. And so what we're going to do is backpropagate through this big, long, unrolled computation graph. And I want to note a couple of things. So first, the parameters that we're using at every time step are the same parameters. So that W that we had in the recurrent neural network is the same W whether we're at the start of the sequence or at the end of the sequence. Now, you could actually imagine having different W's at the beginning or at the end of the sequence. But then you wouldn't have a recurrent neural network. You would have something else. And you'd also have a problem, because this sequence could potentially extend forever. And we wouldn't then be able to train. We don't have any sequences that are infinitely long that we could train these parameters on, much less a lot of sequences that are infinitely long. So it's crucial if you want to really be able to deal with arbitrarily sized inputs that we have this kind of parameter tying. So another thing to note, when you read the literature about recurrent neural networks, you're going to sometimes see the phrase backpropagation through time. That's all this is. It just says we're going to unroll things, and we're going to propagate errors backwards using the standard backpropagation algorithm. And there's nothing special about it. So what do I mean just explicitly by parameter tying? So let's look at this parameter u up here. So this is one formulation of the recurrent neural network. So we can think about u as being a value that contributes to computing h1, h2, h3, and h4, where all of these are using the very same u. So really there's a single block that links all of these things together. So we don't usually draw these variables when we show computation graphs like this. They're just, we just represent the data flow that is a function of the inputs, because that's what we have a lot of control over, and we leave the variables out. But when we're thinking about what the computer is doing when it executes backpropagation, it's really nice to remember that these things are kind of pointing at sort of all the same positions in the input. So what does parameter tying mean for the problem of learning? So let's consider that we can get errors. We're going to have errors coming in to U from all 4 of these sources. And so the derivative with respect to of f with respect to U is going to just be, we're going to be summing over all of these things. So parameter tying, the derivatives just accumulate when you have multiple incoming edges in the computation graph like this. So parameter tying will have also come up when learning the filters in convolutional neural networks, and it's also present in the transition matrices for HMMs. So when you're making a decision about how you transition from one state to the next, it doesn't matter if you're at the beginning of the sequence or end of the sequence. All that matters is what state you're currently in. It's exactly the same notion of tying parameters. Okay, so I briefly alluded to this, but just to recap, we want to tie the parameters because this also lets us reduce the number of parameters we need to be learning. If we had an independent matrix for every time step, we would have a much harder learning problem. We would probably have too many parameters to learn, and we would overfit the training data. And this lets us deal with arbitrarily long sequences. Now, if you always have short sequences, you might say, well, do I really want to tie parameters? Maybe you actually don't. Maybe you do want to untie them. But then you wouldn't have an RNN anymore. You'd have some other different kind of interesting model. Okay, so this is one way of training a recurrent neural network. We assume that at every time step, we've got some label. We aggregate the losses across all time steps. Another common thing that we like to do is we want to, what I call, read and summarize. So here's the idea that we've got some sequence of vector inputs, and we want to read this whole long sequence, and then we want to make a decision. And these sequences might be something like a historical set of stock prices, and we want to make a decision at the end, should I buy this stock? I don't know. I'm sure people have applied recurrent neural networks to the stock market. My guess is if they work today, they're not going to work tomorrow because you all go and try this. That's one of the challenges about working in a domain like that. But there are many things where you want to read a sequence and get a summary of that sequence and then make a decision. Slightly one that's closer to the topics that we've been talking about this week, you might want to read a sentence and say, did this sentence contain a grammatical error? Was it a good sentence of English or Portuguese? And make a final decision. We can also do that. So we just take the final state of this RNN after we've read the whole sequence, and we then use that to make some kind of prediction. So this is what those of you who were at Graham's invited talk last night, he talked about doing this to do sentiment classification. This is exactly the model he used to decide whether a movie review was positive or negative. So I'm going to give a second view of how recurrent neural networks are working, which is actually, I hope, going to suggest that this is not just something that we can apply to sequences, but is a general purpose tool for representing complex data. So we can think about recurrent neural networks as a recursive construction of a value. So we're computing that HT recursively in terms of HT minus 1, and eventually we've got a base case. But this is crucially stands in parallel to how we define lists recursively. So let's recall how you construct a list recursively in a language, say, like Lisp or in Haskell or something like that. So we define a list in terms of a base case. So we're going to say, this bracket is a list. Specifically, it's the empty list. And then we've got this inductive component of the definition of a list. So we're going to say that T followed by H is also an element, is also a list. So T is going to be a list, and H is going to be an atom. And then the two, where you concatenate them together, is also a list. And so with this definition, we can determine whether something is a list or not. And it's obviously a very trivial definition. It makes a lot of sense. It basically says we can peel things off one at a time. So RNNs work exactly the same way. We're going to learn, or possibly define, a representation of the base case of that empty list. So what was that in our, what was the definition we used for the representation of the empty list? Called it H sub 0, right. And that can be learned, or it could be the 0 vector, it could be some other vector which we might have reason to have. And then we're going to have a representation of the inductive step. And we're going to define, in the case of the RNN, we've got a representation of the prefix T, and we're going to be adding one new element, H, which I probably should have called X here. The reason I called it H here is this is tail and head, so this is like the classic kind of data structures view of this. H gets overused. You run out of letters in computer science. It's always a problem. And so we've got this function, though, that we can compute each time inductively. So lists are really convenient, but we can define trees inductively. We can define graphs inductively. Any problem you can define inductively, you can neuralize in some meaningful sense. So you're going to define representations of the base case. You're going to define some representation of the inductive step that's going to operate on the pieces of the inductive step. And then anything that falls under that definition, which in general, the convenient thing about recursive definitions is they can become unboundedly large. We're going to immediately have a way of defining a neural network representing that object. And that's a really, really powerful way of thinking. So if you're working with some complex data structure and you're like, I'd really like to use a neural network to represent this, rather than looking to see if somebody else has solved the problem, just step back to this recursive definition, and you've got a recipe that's going to work anywhere. OK, so why don't we move on to a more concrete example? Let's talk about language modeling. So the way we're going to, did Biksha cover language modeling with neural networks yesterday? No. OK, good. So what we're going to do is we're going to work with a neural network that's going to predict words at every time step in sequence. And we're going to repeat this process until a special word, a stop symbol, is predicted. That's going to say, you know what, the sequence is over, just return it to the caller. And what we're going to do at every time step is we're going to have some hidden vector h, and we're going to use that to define a distribution, a probability distribution over the next word. Now we don't know for certain at any point what the next word is going to be, so we want this to be a distribution. But what we are going to assume is that we have a fixed vocabulary, so just all the words in English. Think about it as the dictionary, and each one of them is going to have some probability associated with it. And the way we're going to do this is we're going to take this hidden vector, which is going to be, say, d-dimensional, usually some small number of dimensions, 200 or 500 or 1,000. And we're going to have a vocabulary of, say, 100,000 words. And we're going to project this hidden vector out onto this 100,000 dimensional vocabulary, and then add a bias to it. You can think about the bias as just being like how much do we like certain words. So there are certain words in every language that are very frequent. In English, for example, the word the or a is we use it a lot. It's probably going to have a fairly high bias. And then other words maybe are going to be generally infrequent and will have low biases. Okay, one quick question just to make sure you're paying attention. What are the dimensions of W? If we have a d-dimensional vector and we're projecting this out onto a 100,000 dimensional vocabulary, how big is W going to be? Yeah, 100,000 by D if you're talking in sort of column major order. If you have column vectors, and D by 100,000 if you prefer the other way. This is a problem with linear algebras. Nobody can agree which is more important, rows or columns. Right. And the dimensions of B, they're also going to be 100,000. Okay. Once we've done this projection, we've got this vector U. I call it U for the unnormalized probabilities. Often in neural network code or in libraries, you'll see this referred to as the logits. And we're going to pass these through a softmax transformation. This is just going to take that vector of real valued numbers, which can be between minus infinity and plus infinity, and normalize them into a probability distribution. So that means every single one of them is going to be greater than or equal to 0, and they're going to sum to 1. So that's a convenient form that lets us do this. Okay. So now the task is going to be, so this tells us if we've got an H, how to turn that into a probability distribution. That's going to be the workhorse of our language model. Now the question is, how are we going to get a series of H's to predict each word subsequently, and how are we going to justify the construction of a probability distribution for individual words that matches in some sense the probability distribution of a whole sequence, which is language isn't just individual words, it's sequences of words. So let's think about what the probability distribution of a sequence is. So we've got a sequence E, and for any set of random variables, E1, E2, E3, we can use the chain rule for probability to decompose them. And we basically can just take one random variable and sample it, and then conditional on that, we can sample another one, and then so on, and repeat this process. So we can do this in any order, but in language, it's conventional for us to think about generating language from left to right rather than, say, from right to left. We speak from left to right. Most of us write from left to right. No, it's a sort of a there's this idea that some words come first, and we're going to condition on the past to predict the future, but you can't actually generate in any order. The chain rule always holds. So we can think about these things as each of these conditioning contexts that we've got, the things to the right of this conditioning bar, as histories. So we can think about them suggestively as history written like a vector H at the beginning. And so what we're going to do is we're actually going to encode these histories in our recurrent neural network language model using a recurrent neural network, and use that to construct our history. And there are a whole bunch of, this is a very nice fit to the problem because we're able to, the thing to note is if we have a long sentence, we are going to still be able to represent the full sentence or the full sentence right up to the end using a recurrent neural network, because there's no upper limit on how much information we can condition on. If we had, say, separate parameters for every prefix of a sentence, eventually we would just have so many parameters. We couldn't fit them all in memory. But a recurrent neural network always just says, well, you've got your W matrix, you've got your V matrix. We're going to also have this new one that does the projection. We're going to have a couple of biases, and that's it. And if you find that the model isn't fitting the data well, we've got an easy solution. We just make the networks bigger, and we try and we see if we can improve things in that way. Whereas in some other methods, the data sort of determines how many parameters we need. And so it's nice to have those two things decoupled. It's very practical. So let's look at how this specifically works. So here's how we're going to build a language model. So we're going to start, when we generate a sentence, with a special symbol that says start. You will have seen this last week in Noah's lecture. I promise all of these various lectures, despite sort of focusing on different elements, are actually very closely related to each other. We had that same start symbol that exists with probability 1. We're going to convert all of our symbols in this. We're going to embed this by converting it to a vector. What does it mean to convert a vector? It just means every vocabulary word is going to be associated with some real valued vector of dimensionality d. These are going to be parameters just like any other in the model. That x vector, x1, is going to be fed in and used to create the initial state of the recurrent neural network, combining again with this h0 vector that is our initial case. This is then going to be projected out using that projection out to the vocabulary, the matrix we just talked about, and we're going to have then a probability distribution. And at this point, we can do something like sample from this probability distribution. This is how we use a neural network as a generative model. We've got a probability distribution, we can sample from it. So let's say we pick the word Tom. And effectively what we're doing here is we're conditioning on everything that this hidden state encodes. So what does this hidden state encode? Well, the only thing it encodes at this point is the fact that this is the start of the sentence. So we've now generated the word Tom. And now this is where RNNs for language models look a little bit different than the other RNNs. We're going to take the thing that we've sampled, the one word that we've sampled, and we're going to embed it and feed it in as the input at the next time step. So we're going to now embed the word Tom in our vector. It's going to be this lookup, and we're going to feed that into the RNN's dynamics, and we're going to compute a new hidden state at time 2. We're going to project it out onto the full vocabulary, and we're going to get a distribution over all the words in the language, and we're going to sample a word, say likes, and we're going to get the second word in the sentence. And when we sample the second word in the sentence, this hidden state crucially remembers not only that we had this starting symbol at the initial step, it's going to know that we had Tom as the first word of the sentence. So we're conditioning on start of sentence followed by Tom likes. So in principle, this RNN has a lot of information. It remembers everything that's come before. So we're just following the chain rule by this construction. Now we can also do this one more time, and we say sample the word beer. And so you can imagine that this neural network has figured out that there's this guy Tom. He likes things, and one of the things he likes is beer. And so all of this lives in the parameters of the network. And we're going to keep repeating this process until we sample a special stop symbol. So in language modeling, we often use these sort of quasi-XML-like tags, slash bracket s, angle bracket s, or bracket, angle bracket slash s, to indicate the start and stop symbols. These are just tokens in the vocabulary like any others. So sometimes when people encounter this for the first time, it's a little bit confusing that you both have these recurrent connections that link the hidden states, and you also have these connections in some sense in the graph that link the sampled words into the recurrent network at the next time step. It seems like in some sense this information is redundant, right? The thing to keep in mind is that this hidden state summarizes what's happened before. It doesn't tell you anything about what the model is actually being used to do at that time step. So the fact that we chose Tom as the first word in the sentence, we could have also sampled a different name, Andre, or we could have sampled the word the, or something like that. And we don't want to feed in, we don't want the hidden state to track what could have happened. We want to actually have the hidden state track what did happen. And so this is a somewhat subtle distinction, but it's very important to not be intimidated. And so if anything is unclear, please do ask. Yeah. Yes, exactly. So it's a vector of, say, length 100,000. So these are big vectors. This is one of the problems with modeling language with neural networks is you have a massive number of parameters because for every element in that vector, you've taken when you did the projection from the hidden state out to that vector, you've taken an inner product with the hidden state and a vector representing each word in the language. And if there are 100,000 words in the language, that's a really big matrix that you've used to, that's a large number of parameters you've used to represent all of this, all of these words.
And each element in this vector is representing the probability of the word in the vocabulary?
Yes.
Being selected?
Yes.
And then we are going to pass this vector as the input for the next?
No, yes, very good. So we've got this vector. This is 100,000 long. Let's say, here is Tom, and Tom has, 0.1 probability, and the has 0.8 probability, and, well, we don't have much probability left to play with, so all of these things, if you add them up, they'll sum to 1. We're then going to say sample from this. So we're actually going to execute, so if we were actually running this in code, we would call a sampling algorithm, which would roll a die, and it would pick from among all of those different elements of the vector proportional to the probability of that element. But in practice, what we're often going to do is we're not going to sample ourselves. We're going to say, the universe has provided us with some language data. We go to a corpus, and in some sense, it sampled. What we're trying to do is figure out we're going to assume that the universe was using this process to generate the data. So we knew when it sampled the first word that the result was Tom. And so we don't always actually execute the sampling step ourselves, but we do, but in general. And so we only pass, though, the result of what was sampled into the next step. We completely forget this softmax after this vector of 100,000 things at the next time step and just take the single word that got sampled. Does that make sense? Okay. Yeah.
The result of what was sampled, is it the probability of Tom, or is it one?
It is a one-hot vector. Yeah. So by one-hot vector, I mean we're going to we can view a single word in a language that we observe on the page. We can encode it in a whole bunch of different ways. I mean, we could use a sequence of characters. We could view it just as like a picture. We can also say every word has a position in this vector of 100,000 things. And if we see a particular word, we put a 1 in that slot, and we put a bunch of zeros elsewhere. That's called a one-hot encoding. And that is what we're going to pass in. And so actually, if you think about all of these arrows here, except for this funny little operation with a squiggle on it, which means sample from, you can think about those as matrix multiplies. And so when we get this embedding of Tom, when we get Tom sampled, that's a one-hot vector, and we're going to multiply it by a matrix. And if you multiply a matrix by a one-hot vector, all you're doing is selecting a single column out of that matrix, right? And so that's the word embedding. So you can think about this like looking up the embedding of a word, selecting a particular vector for a word as either a lookup in a table or as this like matrix vector product. But yes, crucially, one hot.
I also have another question just jumped in my head. Maybe it's very naive, but what if we say it like pairs, like 2, we decided 2 or 3, the most probable words, and keep that information?
Um, s- I think that's an interesting question. There's sort of two aspects to it. So one is we might have the model contemplate at every time step, you know, what are sort of likely things that I should say, and maybe use a little bit of extra processing to sort of imagine what it would be like to continue with each of those when it's working out its probability or updating its internal state. But at the end of the day, we're about to talk about how we train the parameters of these things. And at the end of the day, you just say one word at a time. So we either say Tom, or we say the, or we say Andre, or any of these different words that might get said, and we have to pick one, because that's how the universe works. We might imagine another universe where things work a little differently, but so that's to a certain extent where the one-hot representation comes from. Now, in terms of the way the brain works inside of it, there's a lot of actually really compelling evidence that we are thinking about different ways to process things. So when you're listening to me blather on up here, you're actually anticipating a little bit about what I'm likely to be saying because you're trying to understand me as easily as possible, and your brains work faster than my mouth. So you're thinking ahead. And we might imagine building models that look very much like what you just talked about, where we're saying, I'm not going to do a bunch of processing on everything in the vocabulary. I'm going to think about what the most likely things. So an anticipatory model. But that's very advanced modeling. Like that might be, you might discover the sort of future of language modeling with that. But there will still always be a one-hot component somewhere in there, which is the thing you've actually said. Anything else? Okay. Oh, quick question, yeah.
Why the softmax? I mean, the softmax is everywhere, but it's just like a monotony throwing functions, and so we want to one-hot in the max. I mean, the softmax is always like, it's just like extra computation and nothing.
So the softmax is useful because we don't, what we want here is a probability distribution. So what we want is a function that converts from this unnormalized vector of probabilities. So I'm actually eliding a little bit from this material. We had really this other vector before this, which we called U. In the previous step, which was the unnormalized probabilities, and then we convert that to a probability distribution. Now you can convert you can generate a probability distribution in a whole bunch of different ways. You could say square all of the elements of the vector, add them together and renormalize. That would also guarantee that they are all greater than or equal to 0 and sum to 1. You could do anything you wanted, really. It turns out softmax has a number of useful properties in terms of if there are, so if you view the, so softmax is optimal in the sense of the expectations of the, under the, if you think about a linear model that parameterizes the inputs to the softmax, the expectations of the features that go into that linear model under the softmax are, if you want something where the entropy is maximized when you maximize the, when these expectations in an empirical set of data match the model's data, you want to use this exponential form. Now, we don't actually use real features here, so this justification isn't quite as important, but it has these convenient information theoretic properties. And people generally work with this. But the main thing we want is to get this to be a probability distribution. We don't want to just pick a max. And that's the reason we use a softmax, because we need a full probability distribution. We don't just need a technique for picking the max, because we're going to be fitting this to real language data, and I might suddenly say some random kofevi, And you know, you guys don't, your heads don't explode when you hear, you know, that word. Although a few heads might have exploded that day. Sorry, our president is kind of silly. And so the point is, we have to account for even the unlikely things, and we don't want to just know what the very max is. So that's why we use a softmax at the end of the day. Okay.
I just think that what he was mentioning is that in this particular example, you want to substitute this choose com, for instance, you don't need to know the probability of com, right? You just need to know the com is the highest score.
Oh, yes. So when we go to if we wanted to actually find the most likely word at that time point, we wouldn't need to do the softmax. We would just work with that U vector.
So basically, if you do this model, you do the softmax.
Well, if we wanted to actually run the sampler and be able to generate things, the input to if you have a sampling algorithm for a categorical distribution, you know, that's the thing that simulates rolling the 100,000-sided die, it's going to take a probability distribution as input. So you do need that softmax. And if you're going to be training this thing, we're going to need that probability as well, because we're going to be maximizing the probability. So for those two cases, yes, we do need it. If we're doing something like maximizing, trying to say what's the most probable sentence, well, that's actually going to turn out to be really hard. But if we're saying, okay, given this prefix, what is the most probable next word? Yes, at that point, we don't need a softmax. We just can compute the max over that thing. Okay, I think some of this is going to get a little bit clearer when we talk about language model training. So in the interest of getting through all of these things, let's move on to that. So here we've got this sentence that we've generated randomly. But in practice, what we're going to do is work with a corpus that's going to contain sentences like Tom likes beer, but it's not going to contain sentences like Tom likes wine, because maybe Tom doesn't like wine. And there are going to be a whole bunch of these things, and we're going to want to estimate the probability. We're going to want to estimate the parameters of this model such that the likelihood of the corpus is maximized, or another way of saying it is the cross entropy between the empirical distributions of the corpus, of the sentences in the corpus, is minimized with respect to the model's distribution that's being defined. So this model here defines a probability distribution over all sentences. And some of them are going to be highly probable, some of them are going to have low probability, and so this cross entropy is just a way of comparing two distributions. And we don't usually think of corpora as distributions. At least I feel like that's not a common way of viewing things in the modern world. But it really is the case that, you know, there's, you know, 1/100,000th of the probability of 100,000 sentence corpus is this sentence, and you know you've got some other probability elsewhere. And so the cross entropy loss just says we want to compare those two distributions using a cross entropy criterion, and we want to make that as small as possible. And if the model doesn't make that cross entropy very good, well, we're going to adjust the model to do so. So the way we're going to do this is we're going to assume we've got this sentence, Tom likes beer. This is our training sentence. And now, notice we've now got this gap between this probability distribution, the softmax that was predicted, that's caused so much consternation, and the actual word that we've observed that the universe has sampled for us. And we're going to compute a cost between these two things. So this is looking very much like the training procedure that we talked about right at the beginning, where every single position in the RNN is labeled with something and has a cost. And in particular, we're going to use the log loss or cross entropy loss. So we're going to take the log of the probability of Tom. So Tom is going to be, as our first questioner asked, that's going to be one little slice of this vector up here. We're going to go in that cell, and we're going to compute the value, and we're going to take its log. And that's going to be, and the negative of that log is going to be the cost that we've suffered. And we're going to try and minimize that. And we're going to then aggregate all of these costs together. And now we've got something that we can run backpropagation on. And we're going to backpropagate the errors. and we're going to adjust all of those W's and U's and B's and C's that we saw in the parameters, and we're going to do this, and this is going to optimize the probability of the sentence. Now, in practice, this is how you do it for a single sentence, and we want to train a language model on a whole corpus. So what we're going to do is we're going to assume that all of the sentences in our corpus are generated basically at random from the same model. And so we're going to be able to add their log probabilities together. They're independent and identically distributed. Now, in language, do we really think sentences are independent and identically distributed? Is the sentence I'm about to say independent of the sentence I just said? No, not really. So you could imagine a much more complicated model that tries to treat language as one giant sequence. You're going to have trouble learning that model, though, for a variety of reasons. So this is the standard assumption that we make, and we're going to then train this model. Each of our training instances are going to be a single sentence, and we're going to alternate, and we're just going to randomly move through the corpus and feed in sentences. And and we're going to do this until we've minimized this cross entropy. So let me say a few words of comparison to other models of sequences for language that have been proposed. So the traditional models that have been used for language modeling are based on a Markov assumption. So the idea is, rather than trying to remember that whole history that you get out of the chain rule, where you just remember more and more and more, the idea is you just forget after a certain point things that happened a long time ago. And this is a really important assumption, but I think RNNs are more powerful because language has a number of things that are useful to remember that often happen quite remotely in the sentence. So if you started a sentence with a question word like what, it's probably an indication that when you get to the final punctuation in the sentence, you better predict a question mark. And if you sample words from these models that are trained and compare a recurrent neural network to a Markov model, you will in fact see that the RNN is very good at learning this correlation between, if you start with question words, you better end with question marks. There are other things that are very obvious, like if you open a parenthesis, you better close it later. And you better not, you probably aren't going to open multiple ones unless you're modeling something like source code. And if you do, you better close as many of them. If you're training your RNN to generate Lisp, it's going to learn how to balance parentheses. So these are things that Markov models just forget because of their construction. Yeah?
In the previous slide, the input vector of one step, is that real word, the real previous word, or is that?
It is the real word that the universe has sampled for us. So yes, it's just like during the sampling procedure, except now at training time, in some sense, we're outsourcing the sampling procedure to the universe, and we're saying we just want to fit this data. But at every time step, so at H2, we want H2 to encode not what could have happened, but what actually did happen. And so we feed in, the first word of the sentence. Yeah? Yes?
Although it never forgets in some way, this is based on a kind of a first order mark of the sample.
It is.
It also makes sense to have it like second or third order, or you can have the previous of the previous?
Yeah. Okay. So that's a subtle question. So we're going to come back to this right after this and talk about how we basically get these models to remember longer term things. So it's true that at every time step we're only feeding in the previous symbol, but that H, if we assume that H is doing its job, it's able to remember relevant information from far back in history. And so in principle it can, but yes, obviously, especially if you think about the gradient flow, if you make a bad mistake about predicting the next word and you want to update the parameters, well, the gradient doesn't have to go very far to get back to the current input. But if it has to go back a long way, there's no direct arrow pointing back to, say, a word at the beginning of the sentence. You've got to follow all of these steps. And that's going to cause some problems. So yeah, there are variants that actually feed in at every time step. Some of the a number of recent tokens. It's kind of an empirical question whether they work. Most of the work, though, has not been on sort of changing what we feed in at every time step as much as trying to improve the model's ability to remember things from the distant past. Let's see. Yeah, there was another hand, but yeah. Oh, great. All right. That's all the questions then. Okay, so let's go on to talk about training challenges. So what happens to gradients as you go back in time? So here's our F. So I know this looks like the read and make a decision example. This is actually embedded, though, in RNNs as well. So when you're making a decision about how to predict the fourth word of a sentence, so yeah, it depends on the current inputs, but it also depends a little bit on the first inputs and even on the initial state. And so we want to be able to compute derivatives with respect to all of that. Yes, there will be other losses that are in there. I'm just not showing them. So let's imagine we're down here at the end, and we want to see how gradients travel back in time. So we're interested in getting a derivative with respect to this loss f. So first thing, derivative of f with respect to itself. We know that. That's 1. Now we can just use the chain rule. We can say, well, what's the derivative of f with respect to this prediction y? Well, that's the df dy. And now the chain rule just says we're going to multiply this. If we want to know what the derivative of f is with respect to h4, well, we're just going to multiply this by the derivative of y with respect to h4. And now if we want to know the derivative of f with respect to h3, well, that's just multiply that whole thing by the derivative of h4 with respect to h3. Go back further in time, h3 with respect to h2, and so on. So now we can actually get a derivative with respect to h1. And we can continue down into these other components of the model as well. But I want us to focus on this temporal component where we've got these, basically chains connecting the HTs, right? So we can note that here we've got this little sequence of HT, derivatives of HT with respect to HT minus 1, looping from t equals 2 to 4. And so in general, what we're going to have is if we want to get the derivative with respect to h1, we're going to have this product here where we're taking the derivative of ht with respect to ht minus 1 up to the length of the sequence. So that's going to grow with, basically we're taking a number of products, we're exponentiating something effectively, and the exponent is the length of the sequence. And sequences can grow unboundedly, and what happens when we exponentiate something in an unbounded way? Well, let's look at that a little more closely. So what are these derivatives? What do they look like? What does dht, dht minus 1 actually look like? So let's replace this function vxt plus uht minus 1 plus uc with a symbol zt, just for analysis purposes. We can now rewrite this component here as follows. So we're just saying first we're going to compute the derivative of ht with respect to zt. Now we're going to compute the derivative of zt with respect to ht minus 1. We're just breaking this up into 2 steps because there are these two. We first do this like linear combination of the features, and then we do a nonlinearity. So we're just breaking the evolution of ht up into these 2 steps because that's what the model does. So the derivative of ht with respect to zt, that's just saying, what is the derivative of this nonlinear function? Well, that just depends on the nonlinear function you've got. So, if you're using a tan h, it's going to be one thing. If you're using a ReLU, it's going to be something else. But all of them are going to be diagonal matrices. So the derivative of a vector with respect to a vector is that Jacobian is, of course, going to be a matrix. But because we're assuming that we've got a element-wise nonlinearity, if you make a change to the derivative with respect to of one element with respect to any other is just going to be 0. So that's why it's a diagonal matrix. So we'll write it like this. So what is the derivative? Just a quick linear algebra check. For those of you who like matrix calculus, what's the derivative of zt with respect to ht minus 1? U. Very good. You guys did the lab. Okay. So what we've got here is the derivative of ht with respect to ht minus 1 is this, which is just this diagonal of the derivative of zt times u. All right. So we've now got this constant here, and we've got this thing here. So there are 3 cases to consider. So if you take so U is a square matrix. So we're basically taking a square matrix and we are multiplying it by itself many, many times. So we'll ignore this component for now. And there are 3 cases when you do this. So the largest eigenvalue of U is exactly 1. And in that case, basically, this gradient is going to roughly stay the same in value as you propagate along this chain. Second, if that largest eigenvalue of the U matrix is less than 1, then the gradient is slowly going to disappear over time, and it's going to get smaller. Which is good because if the largest eigenvalue is bigger than 1, then that gradient is going to get bigger and bigger, and soon you're going to have infinities, and your numerical optimizer is going to break. So this diagonal, the gradients with respect to the nonlinearities we use tend to be less than 1, and so basically we tend to dampen the eigenvalues with the presence of that. So we tend to have in RNN modeling this first problem, where gradients just get smaller and smaller as you go back in time, and you can't actually get any information back. If you make a mistake about a prediction at the end of a sequence, you can't actually tell the beginning of the sequence, hey, could you please change your parameters so that I can make a good decision at the end. They just kind of forget over time. They tend to be very forgetful. Okay, so what this means that in practice, long-range dependencies are difficult to learn, although in theory it's possible if you get lucky. So some of the solutions that have been proposed are just use better optimizers. Maybe you don't need a very precise gradient. Maybe you just need some algorithm better than SGD that responds to very small gradients. You can also normalize the gradients to basically say, well, sometimes they're going to get small, sometimes they're going to get big. We're going to kind of normalize them so they're all roughly the same size. The problem with that is you've got big gradients coming down from the prediction at the beginning of the sequence with respect to the inputs to the beginning of the sequence. And then you've got this tiny little whisper going on in the side, which is what the end of the sequence thinks about the beginning of the sequence. And so normalizing both fairly is incredibly difficult. A very popular thing that actually works surprisingly well is to at least initialize your matrices so that these spectral radii of the matrices of these U matrices, the square U matrix, is roughly 1. is actually really useful, and there are a bunch of techniques for generating random matrices that have spectral radiuses of 1. And this actually works really well. Now, during learning, they immediately diverge, but this is often enough to kind of get going. There was actually the suggestion made, maybe we should, instead of feeding in just the most recent symbol, maybe we should feed in a few more recent things. Maybe we could even feed in things from the distant past. That's actually another interesting idea. And there's an adaptive way of doing that that we're going to talk about in the second half of this lecture called attention. But the most interesting, the most standard solution that people have been working with are alternative parameterizations of that recurrent cell. So rather than just using this matrix multiply, we're going to do something else. And these are things called long short-term memories or gated recurrent units, and they're sort of family and friends. So we're going to talk about those. So long short-term memories were proposed in the mid-1990s. They languished in obscurity for quite a while, and then suddenly they became the most popular thing ever in the last few years. You can't read a paper without seeing them mentioned these days. They're a bit heavy. We're going to go through the derivation and see all of the complexity that goes into them. And so there's been this constant search for things that work as well but don't require as much computation. So Kengyang Cho, who's tonight's invited speaker, I highly recommend his talk, invented one such alternative called a gated recurrent unit. And the intuition here is, so we saw the problem that we got with that, when we took the derivative of ht with respect to ht minus 1, the problem was we had this matrix multiply. And so as we went back in time, we just repeatedly multiplied by this U matrix, right? And that is what led really to the vanishing gradient problem. And so what we want is the error signal, the derivative with respect to the error, to be roughly constant across time. That is, we want a function whose Jacobian has a spectral radius of exactly 1. That is, we want the identity function, really. So here's a way that this roughly corresponds, I think, to the way Schmidhuber, who invented LSTMs, was thinking about this. So we can do this as follows. So imagine, let's think about rather than thinking about H, let's think about C, a memory cell. What we're going to do, one thing we could do is instead of we could basically create an additive cell where we take the previous ct minus 1 and we're going to add some function of f of x to it, and that's going to be the updated contents. And this f of x for the next few slides is just going to be our favorite tan h, with a linear transformation or affine transformation inside of it. So then we can say our cell is then converted to the hidden, to this sort of squashed hidden thing, because in the classic RNN, all of our values were between 0 and 1, so we want this to be, we want to have that nonlinearity in there. So one thing to note here is the derivative of ct with respect to ct minus 1 is just I, right? Is it clear why, from this definition of ct, why that's the case? So f of x doesn't depend on ct minus 1, so the derivative with respect to that part of the function is 0. And the derivative of ct minus 1 with respect to ct minus 1, well, derivative of something with itself is just I. So we're good, right? So what do you think about this? What, do you see some potential problems with this model? What's going to happen to the contents of the memory cell probably as time progresses? They're probably just going to get massive, right? You keep adding things. You never take anything away. It would be like you could never forget anything. The other thing is, do we really think that when you learn something new, do you just remember it purely based on the inputs and it's not really dependent on what you already know? It's also not a very satisfying thing. But we've got this beautiful constant error propagation. So we have solved that problem. But this doesn't work at all for those reasons. So here's something that we can do where we basically are going to update the contents of the cell, but now we're going to also look at the HT-1 when we decide how we're going to update the contents of this memory cell. So now the derivative is, you might say, almost constant. So we've still got this I term in there, but we're also going to be adding a little bit of noise onto this Jacobian. So there are going to be some off-diagonal elements. Yeah, they could cause some trouble, but at least we're adding an I to that Jacobian. So there's a strong incentive for the thing to at least stay somewhere around the sort of a spectral radius that we want. And this is a more flexible form of the function. So we're now no longer updating our memory just based on what we're currently hearing. We're also thinking about what we already know and deciding, well, do we want to make changes to sort of the current state? Are we hearing something that's new? Or are we hearing something that is maybe something we already know, in which case we can just have an update of 0. So you can imagine doing some sort of general stuff. However, we still have this problem that we're constantly adding. F of x is delivering values between +1 and -1. Okay, maybe we're lucky and they're going to be kind of oscillating between sort of reasonable values. But in practice, the values of these memories are going to diverge. So what we're going to do is introduce a mechanism for forgetting. And this is one of the really cool innovations about LSTMs. So this I know it looks like kind of scary stuff, but it's really straightforward. So the idea is we are imposing something called a forget gate. So this ft here, this is a vector, and it's exactly the same size as ct. So we've got, for every element in the vector, a gate. Or this forget gate, so we've got a scalar for each of these things. And the scalar is a value between 0 and 1. And it's computed by this function here, which is some linear function of xt and the previous hidden state passed through a logistic sigmoid function. Now that's that sigma there. That logistic sigmoid function, that's the S-shaped function that maps between 0 and 1. And so this is intuitively what this means is that for every cell we can decide, do I want to keep with this value and preserve it, or do I want to reset it to 0? And we can knock out individual elements of the cell. Oh yeah, but crucially, this dot with the circle with the dot in the middle, that's what the notation I use for element-wise multiplication. So we're just going to go through each element of ct-1, and we're going to scale it down by some number between 0 and 1. Intuitively, if you want to remember it, it's going to have a value of 1. If you want to forget it, it's going to have a value of 0. How do we learn? How do we know whether we want to remember or forget something? Well, we're going to learn that function, f of f. The model's going to learn what to forget. The second thing we're going to do is impose an input gate, where we're going to do the same thing, except we're going to decide how much of the input do we actually think is important. We're going to compute some values, and maybe not everything that is coming out of this is going to be useful. Maybe we already know things, for example, and the input isn't telling us anything interestingly new, so we don't need to update our memory cell at all. So those things can get zeroed out. And again, how are we going to learn? How are we going to know what things we should input and what things we should just ignore? I think maybe a better name for this would actually be the ignore gate. We are going to learn that as well. So this is, I don't know what this model is. This is like something that's it's almost to an LSTM. LSTM adds one more component. It adds an output gate. And it basically says, I'm going to compute one more gate that is going, when I compute the hidden state, which is just this nonlinear transform of the memory cell, I'm going to limit how much access, how much you can manipulate, how much the caller of the LSTM and subsequent steps can see from that step. And that value is going to be controlled by this output gate OT. Yeah.
Can I just quickly ask this F up there, what is it, how is it different for the input gate, how is it different from the Fi down there, which is inside which is the sigmoid function?
The F up here? So all of these Fs are linear transformations. They're just take Wx plus B and you've got a set of learned parameters. And they're subscripted just to indicate they're going to be separate sets of parameters. So up here, the memory cell is not, we don't pass the update of the memory cell through any kind of squashing nonlinearity. We just have some direct linear function of the inputs and the previous hidden state. And then for these, we want them to have a value between 0 and 1 because they're gates, right? So that's whenever you see the logistic sigmoid these days, you're either trying to build a probability between 0 and 1, or you're trying to build, a gating where things are squashed into that range. So this output gate is the kind of last innovation that leads, and this is actually an LSTM. Yeah.
Does the recurrent construction of this model not imply that the time dependencies will weaken as the distance increases?
It does. But we still crucially have this addition. So remember when I've derived this. So from the previous slide. So we started with this additive form here, where we're adding something to the previous memory cell, which is kind of the update to the new memories. And if we have exactly this additive form, the derivative as we go back in time with respect to sort of things from the distant past is going to be constant. And that's the thing that we want to be present. That's the dynamics we want this model to have in order to facilitate the learning of long-range dependencies. We want to keep things as close to I as possible. And so we weaken this in a variety of ways. We add these off-diagonal terms, where this is going to be, in general, a little bit bigger. And here, we're now going to have a little bit of weakening at every time step based on what's being forgotten. So you can think about the effect that this forget gate and the input gate is going to specifically the forget gate is going to have when we are thinking about the derivative of of CT with respect to CT minus 1. It's going to be scaled by the value of that forget gate, right?
So in the context of your previous earlier example about the likelihood of snow tomorrow, for instance, we know it tends to snow during the winter.
Yeah.
Would this sort of implementation be able to condition on the fact that it is winter and it did snow 12 months ago? I think this is the same question, but it's trying to get it more specific.
I see. So there's nothing in this model that makes it easy to learn regular periodicities. So we don't know. The model can implicitly learn to, or if it works really hard, you can train it to kind of discover that there's this regular time, sort of regular phase that things are occurring in. These models aren't particularly good at that. There are extensions of RNNs that do have some knowledge about recurring events, or that's actually kind of an interesting open research area. People have proposed a variety of things. In principle, though, if you do daily predictions, an LSTM can establish connections between something that happened 365 steps ago and something that happened 365 steps in the future. So it is possible for it to learn a function that's separated with that many intervening events. So there are, we will So this does make things a lot easier than a regular RNN. It is in principle able to learn that function, but in practice, if you want to rely specifically on periodicity, it's going to have trouble. Okay. All right, so this is our LSTM, where we've got an input gate or an ignore gate. We've got a forget gate, which tells us how much of the previous history to forget. And we've got an output gate, which basically says how much can a caller and the future access a particular hidden cell. It protects those values. This is the formulation of the LSTM. One thing I will point out is I like this particular variant of the LSTM, which is to get rid of one of the gates, or rather, instead of learning a set of parameters for the forget gate, define it to be 1 minus the input gate. So intuitively, what this says is that if you're going to be inputting something, you better correspondingly forget something. So you can think about the LSTM having a fixed size of memory, and when you add something new to it, you better forget something in the past. This often works a little bit better, but it depends, again, on your problem. Okay, here's another visualization of this, and I know it's basically coffee break time. So I think rather than rushing through this, why don't we take the coffee break now, and then we'll come back and talk about grooves, and then you can ask questions about this.
Nice to see you.
Ready? Okay, let's get started. Just because I do, we're gonna run out of time, unfortunately. Anyway, there's so much great RNN stuff to talk about. But first, I do want to have us all briefly take a second to applaud our wonderful organizers and hosts this week. As a speaker, I promise you, they do a lot for us as well, and this is one of the best organized machine learning summer schools. So why don't we thank our wonderful organizers? It's really great. You guys are great too. Okay. Another way of thinking about what LSTMs are doing is by looking at a graph. Like, some people like equations. I like to look at graphs. This is a beautiful figure from this guy called Chris Olah, who's a researcher at Google Brain, and he has a blog where he explains deep learning using some really incredible visualizations. And he's got this little view of a cell, and I think basically this is another good way of seeing things. So the lines in this graph represent data flow. Multiplication says, well, this is a element-wise multiplication. Addition says you've got an element-wise addition. And the thing that I like about this is when you look at how things progress over time, you see this upper line here representing, well, we're at each time step, we're going to be multiplying this by this gated thing that we've computed that's a function of xt. And of ht, and then we're adding to it. So that line running across the top, that's the memory cell that's evolving over time. And we're computing these HTs at each time. And then what we're doing is we're forgetting a little bit of the past. That's that forget gate. And then we're adding some new memories to that memory cell. And so this lets you sort of really understand in a different way what's going on inside of LSTMs. So very quickly, I want to talk about another variance that has a similar kind of additive update to the hidden state, but is a little bit simpler. It's going to use fewer matrix multiplies, which, when you're trying to optimize this code to run as quickly as possible, those are the really computationally heavy things. So we had 3 gates in the previous formulation of LSTMs. Here, we're going to have just 2 gates. And so this is going to be, we're going to have to compute fewer values. So here what we're going to do is we're going, instead of having a memory cell that then gets converted into a hidden state, we're just going to think about a single hidden state variable, and it's going to be evolving over time. But rather than having the hidden state depend either directly or indirectly multiplicatively on the previous definition or the previous time steps hidden state, we're again going to use this additive formulation, which helps us deal with the challenges of exploding gradients because the derivative ends up being something closer to the identity matrix. So basically the top line is the update. So intuitively what we're doing is we're going to be updating the previous hidden state by forgetting a little bit, so 1 minus this gating function zt, and then we're going to be, we've got some update, this tilde ht, which is sort of the new value of the ht, and we're going to say how much of that do we want to put in. That's going to be this gating function zt. So zt is just a standard gate. It's computed just as follows. We've got this f of z, which looks at the previous hidden state and the current input and decides, well, am I going to be updating or am I not going to be updating? It's going to be squashed to be between 0 and 1, standard gating. And then let's look at this tilde ht. This is the sort of new value of ht that we'd like to ideally compute, or how much of the update we want to, or what this sort of update value is going to be. And this is going to be a function of the current input, obviously. You know, we want to, our new memory is going to depend on the thing we're observing, xt, but it's also going to depend on the previous time step. However, rather than just being able to see all of the previous memories, there's also going to be this, what's called a reset gate, which is going to let us like not decide how much of the past to attend to. And intuitively what this is saying is, if you've got some really surprising input, you might just want to tell that network, oh, you know, things have seriously changed here. You better not pay attention to what's in your memory. You better be paying attention now just to the things that are coming in the input. So that's what that RT gate has to do. And so this is a few, you know, smaller number of computations. It tends to work fairly similarly to LSTMs. And it is sometimes worth, if you're working in a performance critical application, it can be nice. So here's a summary. So these are the three sort of definitions of how the RNN's hidden state evolve over time. So the main thing to notice is that you get better gradient propagation when you use addition rather than with multiplication. And so that's what LSTMs and GRUs have. The specific way that they do these updates is you know, architectural dependent. This is still an open area of research. In fact, people are now starting to use automatic methods, reinforcement learning, to discover new architectures and try this out. There was a paper at iClear this year that discovered a new gate, and that gate was weird, or that cell was weird. But it worked really, really well. For a while, it was the state of the art in language modeling. Yeah, so these are the comparisons, and you can use sort of any of these. Yeah.
How does the nonlinearity influence the behavior over with the diminishing gradient? And also in practice, is there any real limit to how long you can really remember stuff?
Those are two great questions. So the nonlinearity does. So for example, if you look at this HT, and we went through what the derivative looked like there. So there was this diagonal term that was in there. And the derivative of the element-wise nonlinearity is generally less than 1. So with the logistic sigmoid function, which is not usually used and not very good, it's strictly less than 1. With tanh, it can be 1, but it's usually much less than 1. With ReLU, it's either 0 or exactly 1. And so learning with ReLUs tends to be unstable because the sort of U matrix tends to be in a range where it's not damped. So actually the damping from the nonlinearity over time helps make the learning a little bit more stable. In terms of getting rid of the nonlinearities, it's important to have them in there for the standard reasons that nonlinearities are important. There are some kind of interesting variants that have been proposed where instead of using a strictly linear model, you use a multilinear model where you have little tensors at each of these steps. So they're a little bit more powerful than a standard linear model. But there's this sort of extra access where you're multiplying, where you're conditioning, say, on the current input at every time step when you derive what the linear matrix is that you're going to multiply by. And those actually work surprisingly well. So you need the nonlinearities, but they help in a couple of ways, both by sort of dampening the dynamics during and making the learning sort of less likely to diverge. That's what I would say the main thing is. Okay, so which one should you use? Well, I'd say actually LSTMs. We just ran a bunch of experiments a few months ago and discovered that if you carefully tune your hyperparameters, a lot of these really exotic architectural variants actually don't do as well as just simple single layer LSTMs, and including this one where we did this complicated architectural search. So people like to occasionally, poke fun at Schmidhuber for, his maybe role in the field, but he really was. This was an absolutely brilliant formulation of a recurrent neural network, and they are really absolutely the state of the art. Okay, if we've had our break, so are there any questions? Okay, let's go on then. So we talked, our motivating example that we went through earlier was unconditional language models. So we basically are just defining probability distributions over language. This is not actually a very useful application. It's more like a fun task to test how good is your learner at modeling the probability distributions one encounters in language. There, however, are many, many interesting applications of what are called conditional language models, where conditional on some input, you generate language. So you can think about many applications. We'll go over some of them in just a second. So this is our unconditional probability. We use the chain rule to factorize things, and we build, basically we use an RNN to parameterize this distribution here. So here's our RNN, so we're always predicting that last thing, conditional on the things that have come before. And you can find this in the slides, but I'm going to jump through. The idea behind a conditional language model is to say, in addition to conditioning on the prefix of words we've generated so far when we predict the next word, we're also going to condition on some conditioning context. And so what we're basically having the model say is, what's the probability of the next word given the history of previously generated words and the conditioning context X. So we might, for example, to go back to, and this isn't just for language modeling, this is a sort of anything that you do with RNNs where, say, we were predicting, what the weather was going to be like today. We can condition on the history of observations, but we could maybe also condition on something, maybe we're going to build, what would we condition on when we're doing something like a weather model? Yeah, that's maybe a slightly odd example. It would be like, what planet are you on? I don't know if you're sci-fi fans or something. Maybe that's not the best example. Let's talk about conditional language models. Shouldn't be too extemporaneous in these things. So here are a bunch of examples of conditional language modeling. So W is going to be our output sequence of words, and X is going to be an input. So we could have a whole bunch of different things. We could have an author, and W could be, give me a model of things written by that author. So you might, a lot of people have written in English. They're going to share a lot of aspects. You know, the grammar, it doesn't change very much between different people, even over hundreds of years. But what people write about changes quite a lot. And this is kind of an interesting thing. Can we build a single model that can generate things that sound like Shakespeare and whoever? We could also build a language model that we say, don't just give me random documents or random sentences, give me sentences about a particular topic, or give me sentences about that are sort of positive or negative. So we could condition on something like a topic label or a sentiment label. We could also do translation in this way, and we're going to come back to how we do translation. So the input X is going to be a sentence in French, and the output could be its English translation. Or a sentence in English could be the input, and its French translation could be the output. We could also do things like condition on something like an image, and we'll talk about this in a second, where we want to generate captions. So we're going to have some kind of representation of the input image, and then we're going to produce conditional on that an appropriate summary. So one thing to note is the input doesn't determine the output. You can do a whole bunch of different things. In fact, conditional on a sentence, sort of you can do a whole bunch of natural language processing. You can do parsing and part-of-speech tagging. And this afternoon, actually, you're going to do part-of-speech tagging with recurrent neural networks, which you can think of as a kind of conditional language model. And so here, you know, you could take a document, you could either summarize it or you could translate it. So all of these things are instances of conditional language models. Okay, so what kind of data do we need to train conditional language models? So in regular language models, all we needed were sentences from a corpus. Now we need paired samples. So we need our inputs and we need the appropriate output. So if we're doing image captioning, we need captioned images to do our training. And one thing to be aware of is it's easy to think of tasks that could be solved by conditional language models, but the data just doesn't exist. So RNNs are not the most efficient learners. If you're in an area where you have lots of data like unconditional language modeling or machine translation, that data just, there's a ton of it. So your task is really easy. But you could imagine thinking about conditional language modeling as a solution for something like dialogue modeling. But we don't really have very many examples in specific domains, at least, of dialogues. We might have a few, be able to go mine movie scripts and find examples of people talking to each other and sort of mimic that. But if we actually wanted to build a useful dialogue system, it's very hard to get enough data in a particular domain. In general, people have focused on using conditional language models with neural networks for a sort of narrower range of topics. So one thing also to note here, we mostly are talking about machine learning problems in this week, but there are some algorithmic challenges to working with conditional language models like this. So we often want to be able to find the most likely sequence of words given some input. And this is actually not a tractable problem. So we can approximate it in a couple of different ways with a beam search, and I'll come back to what a beam search looks like later, or we can draw samples from this by just running that sort of random sampling algorithm we talked about earlier. And so improving this question of how we do search is an open research question. So the main sort of intuition you should take away here is that we've built a probabilistic model, and some of the probability models you've seen earlier this week, like HMMs, came with these very nice algorithms that let you find the max, put this max very, very efficiently, like the Viterbi algorithm. But those algorithms, that Viterbi algorithm, crucially depended on the fact that the hidden states in that model forgot the past very quickly. And that's what let you develop that clever dynamic programming algorithm. Since HMMs never forget anything, we can't use dynamic programming. Or we can, but it doesn't help us. Okay, so this section, the rest of this part is going to look at what's called an encoder-decoder architecture, which is going to learn a function that maps x into a fixed size vector and then uses a language model to decode that vector into a sequence of words x. And the reason I like this is not a state-of-the-art model, but it shows how simple and modular neural networks can be and how you can study, say, vision and image processing on one end, and then you can put this together with a language model which is studied completely independently, and you've immediately got a caption generation system. So an example could be something like this, where we are going to build something that's going to take a sentence, compress it down to a single vector. We might, for example, read with an RNN. In fact, that's exactly what we're going to do. And then we're going to decode with a regular language model. And we're just going to be feeding in, or just at the beginning, instead of using a learned H0, we're going to use the output of that first component as our initial state. And we're going to sample translations of this. And if we train this on good translations, it'll hopefully generalize. In fact, it works pretty well. But we can replace what we feed into this upper part. We can feed in a picture of a dog and pair it with sentences like a dog is playing on the beach. And then you can hopefully feed in pictures of things like what you've seen in your training data, and it will generate captions for these things. So we've got two questions. The first is, how do we encode our input x, whatever it may be, as a fixed size vector c? And this is problem, or at least modality specific. So if you work on translation, you've got sort of your set of kind of encoding techniques. If you work on images, you tend to have different ones. You want to think about the assumptions here that you're making. So a lot of progress in image modeling was driven by the increasing use of convolutional networks. Convolutional networks encode this notion that it doesn't really matter where in the image features occur. So convnets basically slide these filters across the image, and anywhere they detect a match with a learned pattern, they fire. And that's a very useful kind of bias. And maybe that's good for language, maybe it's not. So you want to think about assumptions at this level. And then the second question is, how do we condition on this vector c? I use c to refer to context in this case, in the decoding model. And this is going to be less problem specific, and we'll review a standard solution and architectures for this. So the very first encoder-decoder model was due to Niall Kalkbrenner and Phil Blunsum, actually two of my colleagues now at DeepMind. And they had a very simple idea for doing machine translation. So their X that they're conditioning on, that was a sentence in the source language. They're going to compute a context vector C. And then they had an extra projection there where they created something called S. And then they made a very small change to a recurrent neural network that represented an unconditional language model. So this is exactly the regular recurrent neural network dynamics that we've always had, except now they're adding in this S vector, which represents the source sentence. And then this is just the standard projection up to the vocabulary, passed through a softmax, and then we get the log probability of the next word. So you can see, the difference between this and this is just this one additional S. And so how did they define their encoder? So they didn't bother to read the sentence with an RNN. they actually took the simplest model possible and said, we've got a sequence of words. We can represent them each as a vector. And if we have a bunch of vectors and we want to reduce to many vectors to one vector, what do? We add them. So what do you so who can come up with a problem with this model? Yeah. Word order, yes. Dog bites man, man bites dog. From this model's perspective, it doesn't work. So they also proposed something called a convolutional sentence model encoder, where they ran a series of convolutions over this and built at the final layer an encoding of the sentence. And this is a little bit better. You can capture word order. You still end up at the top layer pooling over a sequence of things. There are a bunch of more interesting extensions to convolutional networks. But this is a little bit better. Basically, convolutions are nice. They learn interactions among features in a local context, and by stacking them, you can get longer range dependencies. And they're also sort of appealing because deep ComNets have a branching structure that's similar to trees, but no parser is required. So you sort of feel like you're getting some of the kind of tree-like benefits of language without kind of all of the problems. So the difficult part, though, is because sentences have different lengths. If you want to use deep ComNets to project them down into a single-size vector, you've actually got to use different numbers of layers depending on the length of the sentence. So there's a follow-on paper that was looking at this stuff. Okay, so that was the encoder. So really, really basic stuff. So then the recurrent decoder is just a standard recurrent neural network language model. So what does this look like going back to our graphical language that we started with? So we're going to start, as always, when we're generating our translation, conditional on the input, with probability 1, start of sentence marker. And we're going to compute H1 like we always did, except we're going to have this S up there, which is this extra little bit of information representing the source sentence. And then we're going to take H1, we're going to project it up onto the distribution over all the words in the language. Hopefully this distribution is going to be more peaked than it is in the unconditional case. The first word in the sentence of a translation, I'm not going to go as far as saying we always know what that word could be. There are many ways to translate any sentence, but we've probably got a much better idea of what it is than if you say, give me a sentence at random. And then we're going to sample from that distribution. So again, say, if the first word of the input sentence is something about Tom, probably with very high probability the first word of the translation is going to be Tom. But if you're a clever translator, you might suddenly decide, I think I can come up with a different way to translate this sentence. And then what we're going to do is feed the word we actually chose, just like with the unconditional language model. We're going to feed that in as a one-hot vector in at time step 2. So we're still feeding in the words that we're actually sampling, and we're doing this again because we don't care what translations sort of in general are possible anymore. We want to know what translation is actually being generated. And then we're going to compute H2 using that representation, the previous hidden state, and we're going to go ahead and feed that S in again. We're going to repeat the process and generate Tom likes beer. And this process terminates. The translation is over when we've sampled the end of the sentence marker. Now, one thing you might notice here is that we're feeding S in at every time step. And this is actually, in theory, we could just feed S in at the beginning and say, you know what, H can remember everything it needs to about S. But that burdens the learner, and it makes it harder to, basically, we saw there's a lot of work to get these models to remember things. And this was written in the era that people had forgotten about LSTMs. And so, they found that it was necessary to sort of provide this information at every time step. But so this is helpful. But in theory, you could just basically replace, say, H0 with S here at the beginning. But they didn't do that. Okay, is this model clear? Conceptually, this is super simple. Okay, so this actually worked surprisingly well. There were some fairly funny example translations. For those of us who had worked on machine translation, we were used to sort of decoders producing word salad, but they were usually related to the inputs. When you start decoding with neural networks, when they go wrong in sort of exotic ways and just produce sentences that have nothing to do with the input. And so there were, but this paper really got people excited about the possibility of using encoder-decoder architectures to do translation. So the next year, some people at the Google Brain Group in California decided to make two changes. First, they had not forgotten about LSTMs and knew that they were sort of strictly better than RNNs. And the second thing they said was, you know what, we don't need to rely on convnets or something silly like addition to encode a sentence. We can just use an LSTM or any other kind of RNN to read a sentence. So we're going to just have we're going to have an LSTM that does everything. It's going to both do reading and it's going to do decoding. And the idea is the LSTM is going to encode things, and at the end, it's going to have a CH pair. So the cell, the memory cell, and its sort of nonlinear projection, which is H, times this output gate. And that's going to be the final state. And that's going to occur when we're at the length of the input sequence. And then we're going to have an LSTM decoder whose initial state is just going to be that pair that we ended with at the final time step while reading the input. And then we're just going to continue, and we're going to do, at every time step, we're going to project HT out onto the vocabulary, and that's going to be our model. So this is a conceptually very, very simple model. In some ways, it's even simpler than the one that came before. The other thing they did was they trained this on large amounts of data, and they used a lot of computational power to do all of this stuff. So here's how this model works. So we're going to read in this sentence in German with our LSTM. So these are LSTM cells. At the end, we're going to have this conceptual context vector, which is really this pair of the cell and the hidden state. And then we're going to feed this in to this as the start state of a new LSTM. We're also going to feed in now, the start of sentence marker here. I've designated that as start. And now we're going to start from those hidden states that this new LSTM is computing. We're going to start sampling words, as we always do. So we're going to sample beginnings, and then we're going to feed that back in, R, difficult, and we're going to keep doing this until we sample the stop symbol. And the interesting thing about this innovation, about this model, is we didn't actually feed in the encoding of the sentence at every time step. We basically just said that LSTM is so good at remembering things, it's going to track what of the input sentence it needs to remember. And the amazing thing is this worked pretty well. It got basically state-of-the-art results in French-English translation. So what are some things we can say about this that are good? Well, this is a simple architecture. That's great. It showed that LSTMs can really propagate gradients a really long distance. So these innovations that we talked about in more theoretical terms were really demonstrated here to have practical value. The distance between, the beginning of the input sentence and the position at which it gets used in the output sentence is quite long. The good thing is also, unlike the convolutional sentence model that Kalkbrenner and Blensom had used, this model didn't resort to getting rid of, say, word order or variable stacked convolutional networks. It could deal, because RNNs can deal with arbitrarily length sequences, it could deal very naturally with those things. So the downside, though, is that the hidden state has to remember a lot of information. Sort of everything lives in C. And we're gonna come back to this very shortly. So there are a couple of tricks, though, that actually I think are worth mentioning about what they did to improve the performance. And so translation, briefly, for those of you who haven't seen this stuff before, is evaluated automatically using a metric called blue. And just, so the more the blue score goes up, the happier you are. So one of the first things they did was they read the sentence, the input sentence, backwards. And then they took the state, after reading it backwards, as the context. And this is a sort of surprising change, because in general, sentence pairs, especially in the language pair they were working with, French-English, they tend to be roughly in the same order. Subjects are at the beginning, the objects at the end. So what this means is, by doing this, the prediction of the first word is very close to where you read the first word of the input sentence. But the end of the input sentence is very far away from the end of the output sentence. Whereas, but the distance, the average distance between word pairs, assuming they're sort of perfectly monotonically aligned, is a distance of n. But some of them are close and some of them are sort of 2n apart. Whereas if you read them both in the natural order, they're sort of, they're closer, or they're always n apart. And so it turned out this was very helpful. And so this kind of suggests that, like, once the LSTM gets going and figures out how to remember stuff, there's kind of this virtuous improvement. This improved the blue score by 4, which, as somebody who worked on translation for years, like, I never got an improvement of 4 blue. Like, that was a really simple trick that seemed, it's kind of hacky, though. But it still shows that these are things that you can do when you're doing sequence modeling. Try reversing things. Another one is to use an ensemble of models. And this is something that is also generally useful when you're making predictions. So when you train a neural network, it's a non-convex optimization problem. You start with some random weights, and you do some hill climbing. And you end up, every time you run your learner, you end up in a different solution. And what can you do if you train 10 models? Can you do something with those 10 models? And it turns out, yes, you can. You can ensemble them. So if you think about what the, normally we feed this unnormalized probability vector into our softmax. But here, let's assume we have j different models. And we'll feed each of the unnormalized probability vectors. We'll compute each of those at every time step using, these are just independently trained models. And we'll take their average, so just their arithmetic average, and then we'll feed that into the softmax. And this turns out to really, really help. So just an ensemble of 2 independently trained models gives you an improvement of 3 blue, and 5 models gives you 4.5 blue. And this is, you can understand this as a kind of variance reduction strategy. So different models are likely to overfit to different aspects of the training data, and by averaging across them, you can reduce some of the variance that's due to those kind of idiosyncratic learning experiences in each of these models. This is always something you can do with neural networks, any prediction task. The downside to it is you've got to run j different models in parallel at test time. So that's unfortunate. OK, so let me say a quick word about decoding. So when we do translation or conditional language modeling, we want to find this most probable output sequence. So we want to find the map output sequence. And so we can write this out as this, so this sequence W is going to have a score whose probability is the sum of the log probabilities, or whose total log probability is the sum of the log probabilities of each position. So we're doing this argmax followed by this sum. And this is a really hard problem. In fact, it turns out it's not just a hard problem with RNNs. In general, it's an undecidable problem. You just can't come up with an algorithm that's guaranteed to terminate. In practice, it usually would, but it's without extra assumptions of like a maximum sequence length. But since RNNs can model sequences that are arbitrarily long, there's no guarantee that with some parameters that any algorithm would terminate. That's why it's undecidable. But fortunately, there's a pretty good solution we can use, which is just a greedy search. So we first say, what's the best first word? And then we say, given our guess of what the best first word is, what's the best second word? And given our guess about what the best first two words is, what's the best third word? And so on. And this actually works incredibly well. There's a slightly better approximation, which is to use a beam search with a beam size B. And the idea is that you're going to keep track of the top B hypotheses. And so what this looks like is as follows. So we're going to have this search state, and it's going to be the partial hypothesis, and it's going to be the score. And what we're going to do is we're going to extend every partial hypothesis, and find the next two best things that according to the model. So at the beginning, where we're starting with just the empty symbol with log probability of 1, we're going to say maybe the best two continuations are either beer or I, and each of those is going to have some probability. In fact, say our model isn't particularly very good and it thinks beer is the best, is the most probable thing just at the first word. So if we were doing greedy, we would have chosen the word beer. Here we're going to choose both I and beer. Now we're going to continue expanding beer, and we're going to get drink and I. And now we've got these log probabilities, and we're also going to extend I and beer. And so you can see if we were actually expanding this tree with the full vocabulary size at every step, this would blossom out to be this absolutely massive tree. But at this step is where the beam search comes in. Now we're going to say, well, we've got 4 things on the stack here, and we're going to just keep the top 2 of them according to their log probability. So here, we have minus 5.8, and down here we have minus 2.87. Now these happen to be on different branches of this tree, but they could have all been on the same branch. And now we're going to continue extending these, so on. And eventually we're going to get to the end of the sentence, and under sort of suitable, there are some obvious termination criteria. We find the thing with the best log probability, and then we either trace back or we just store in each of these partial hypothesis cells the first, the full hypothesis. So here we've got I drink beer as the best translation. So this beam search is a standardly used technique, and if you use a beam search instead of a greedy search, you got a further blue points improvement. So this is useful, and it's worth keeping in mind. Okay, now to give you an example of just how flexible this generic framework is, I want to talk about image caption generation. So neural networks are great for combining modalities because everything's a vector. You can condition on anything because everything speaks the same language. So a quick word about data. There aren't actually a ton of captioned images available. So what people usually do for image captioning is they take data that's used for other tasks in computer vision, like object recognition or object segmentation, and they pre-train the image recognition component of the model. And this pre-training has a lot more data available to it, and then they take part of that model and say this, the representation that model is computing is going to be used as the input to the captioning component. And then they either refine the image model on the captioning task, or even they just fix it and say, we're going to use the representations that were chosen for this other task, and we're going to learn to decode with them. So yeah, often we pre-train on something like ImageNet. Okay, so Jamie Kiros and Russ Salakudinov, some people at Toronto, had a model also in 2013. It looked a lot like Kalkbrenner and Blunsum. It was at NIPS, and they used a convolutional network on the input, and they didn't actually use a full recurrent neural network on the output. They actually used a Markov assumption, but every n-gram conditioned not just on the n-1 previous words in the caption they were generating, but also on the input. And they had this interesting innovation, which I think I'm going to kind of skip over pretty quickly, where they used multiplicative interactions in the decoder's n-gram model. But basically, just so you see how simple it is, they're going to get this context vector x by embedding the image, running a CombNet over the image. And their traditional, so the unconditional n-gram language model just takes word embeddings of a fixed size and builds a big, long vector of those embeddings, and then projects them up to predict the next word, and then samples a softmax. So it's just like a regular language model, a regular RNN language model, except it doesn't actually have this recurrent history. So it's actually a little bit easier to train these things. And back in those days, RNN support and toolkits like Fiano wasn't great, so this let them sidestep this issue. All they did was added a dependency when they computed that hidden state at time t, cx. So they multiplied some transformation of the embedding of the image. And that's, again, just how simple it is to add conditioning on this extra information. And now so we're basically defining the probability of an n-gram conditional on a particular image. So I'm going to skip over this stuff in the interest of time. But basically, they have a slightly fancier formulation of h of x that lets you look at the interactions between the words in the n-gram and the image. And if you're interested, see me or have a look at these slides. Okay, so basically, you can condition on images just as well as you can condition on on text. And this was a vast change in machine learning, where usually the idea that people who worked on machine translation could produce architectural innovations that had, or model innovations that had value for a problem as different as caption generation. In theory, there was this sort of high-level relationship of these things, but in practice, they were so different. We were really changing things so that in practice, you can think about these two problems as being almost the same. Okay. So this, however, at the end of 2014, and I bring this up because this really is a good way to think about stuff, but I want us to also think about how the world changed to get us to where we are now. So there was a problem with all of these models. We were conditioning with vectors. We were representing big things, entire images, entire sentences in a finite-sized vector. And vectors do have a lot of capacity, but they probably don't have enough capacity to represent, think of a sentence from, Melville or something like that. I mean, it's just, insane. In fact, I think Ray Mooney, who, commented on this during the years when everybody was doing this sort of thing, said at this workshop on compositional vector semantics that you can't cram the meaning of a whole sentence into a single vector with a few other, sort of colorful modifiers there. And so people took this seriously, though. So another thing, even if you were to say, Ray, you can make vectors really big, and you can cram all of that into a vector. And so the problem, though, is then still that gradients have a long way to travel. Even LSTMs forget. And you have to do these silly tricks like, reversing the order of the input sequences and all sorts of strange stuff. And even LSTMs do forget. All right, so what's to be done? Okay, so we're going to introduce attention. And attention is a really, really useful mechanism. It lets us adaptively decide how to build connections to components earlier in the input. And we'll see this first with machine translation. So we're going to solve this vector problem by representing the source sentence as a matrix. And then rather than conditioning on a vector when we do our generation, we're going to condition on this matrix. And this is going to solve the capacity problem because that matrix, rather than being a single column vector, we're going to have a variable number of columns dependent on how big the input is. So longer sentences are going to have more columns, and shorter ones are going to have short ones. And we're also going to solve the gradient flow problem even better. So rather than having to sort of propagate all this information along in a hidden state, we're going to make we're going to forge sort of on the fly a direct connection back to the relevant point in the input that should be used to make a decision. Or at least we hope we're going to forge that. We've got to learn all of this. Okay, so let's talk about sentences as matrices. So sentences are of different sizes, but vectors are of the same size, so let's use matrices. So we're going to have a fixed number of rows. This is going to be these sort of some analog to a word embedding, but we're going to have a different number of columns depending on the number of words. And in fact, normally we're going to have the number of columns equal to the number of words in the sentence. This isn't strictly required, but in many of the formulations we do. So how do we construct these matrices? So basically, first, intuitively, this looks like this. So we've got, these like three sentences of different lengths. They're just going to be kind of different sizes. And the question is, how do we build these matrices? And I'll review three strategies that have been used in the literature for constructing these representations. There was a fourth one that came out about a week ago that I haven't had time to update the slides, but I will briefly mention. So the first thing to do is about the simplest possible thing, and it's to represent each word type by a simple n-dimensional vector. And we're going to take all of the vectors for the sentence and just concatenate them together into a matrix. And this is so simple that nobody's really bothered to look in detail about how well or badly it works. I mean, a lot of people have actually tried it, and it doesn't work terribly well in practice. But it's still it's a obvious conceptual baseline that it would be nice to sort of have standard numbers on. So here are the word embeddings for each of these words in the sentence, and we're just going to glom them together to create our sentence encoding matrix F, where the ith column Fi is equal to the ith word vector Xi. So super, super simple. And the size of this is, of course, the number of words by the embedding dimension by the number of words in the sentence. So we can also use convolutional networks to do this. So convnets were designed to process, or they've become very popular for processing, for doing image analysis. Images look a lot like matrices. So we've got these great techniques for learning to extract information that kind of unifies information, and it pulls out kind of interesting abstractions from different parts of patches and images. Seems like we should try doing this with sentences. There, in fact, was a very nice paper in the last few months from Facebook AI Research that showed that you can get nice, you can build sentence representations using convolutional networks to build these sentence representations. So this looks like something like this. We're going to start by concatenating our vectors together, and then we're going to apply some sort of convolutional operation on them. And if you haven't seen this stuff before, don't worry about the details, but we're going to end up with a representation of the sentence that's going to have some fixed number of rows, and there's the function, the number of columns is going to be some function of the size of the input sentence. So depending on whether you're using a pooling operation, you might have things that are quite a bit smaller than the number of words in the input, or there might be plus or minus a certain number of sort of symbols on the end. But by far, I'd say the most common representation these days is to use bidirectional RNNs. So bidirectional RNNs are one of the most useful ideas that have come out of working with RNNs. In particular for natural language processing, I'd say there's really nothing better. If you want a representation of a sentence or to represent a token in the context of a sentence, a bidirectional RNN is absolutely the way to go. And so basically the idea is really simple. We're going to read a sentence from left to right, processing a word in the sort of standard order, and then we're going to have a second RNN with its own independent parameters, although they'll probably share the same input embeddings, and we'll read the same sentence from right to left. And so every word is going to have two representations. One that gives the representation of that word in the context of everything that happened before it, and one that gives a representation of that word together with everything that happened after it. So if we just take the concatenation of those two vectors, or if we add them together, we get a representation of the word together with the sentence. Another thing you can do with bidirectional RNNs is if you take the final state of both of those RNNs, you've got, in some sense, a vector encoding sort of the experience of reading the sentence from left to right, and in the other, in the reverse direction, the experience of learning things from right to left. And we've seen that learning sometimes proceeds it's a little bit easier to learn to associate things in the output model with components of the sentence either starting from left or right. So by doing bidirectional RNNs, you in some sense have the benefits of both. And so if you want a representation, adding together those two final states is extremely useful. And of course you can use GRUs or LSTMs or things like that. And so in this original work, they use gated recurrent units. LSTMs tend to work a little bit better, but because they're expensive, people favor GRUs. So here's what this looks like graphically. So we get our embeddings for each of these words. These are just lookups. And then we are going to feed them into our RNN, and we're going to compute H1, H2, H3, and H4, right? And I'm going to put this arrow above these to indicate that we're reading from left to right with this. And then we're going to do the same thing with a different RNN, and we're going to read this from right to left. And you'll notice the way that I've drawn these things. You know, we've got kind of the stack of three different representations of the word. One that's that doesn't depend on any context, and the other that has these kind of contextual components. And then what we do is we just take these hidden states out, concatenate them together, and build this matrix. And this is the standard representation that's been used for quite some time in translation as our matrix. Bidirectional RNNs are also useful, and I think this afternoon in the lab you're going to be working on part of speech tagging with RNNs. And it turns out that bidirectional RNNs are very, very useful for tasks like that. So if you want to make a decision about what do you think the part of speech tag of this word is in German, well, in general, we want to know not only what the word is, but words can have multiple different labels. Actually, let's pick this one, ein. This can be either a determiner or it can be a quantifier. It can be a number. And so it's ambiguous. But if we know the context that it occurs in, it suddenly becomes much less of a complex question. And we saw that with things like conditional random fields and HMMs, we had to resort to all this dynamic programming complexity to make decisions about how to incorporate context. But by using just these simple bidirectional RNNs, if we look at H3, it's going to capture information in a nice low-dimensional way about the surrounding context. So if we use that representation of H3, of the concatenation of the forward and reverse LSTM, we can make a very good decision about what to label that word. Yeah?
If you concatenate all the image spaces of the matrix, then there must be some limit to it, no? Because I have to, at some point, have weights for this. So there must be a maximum, no?
No, not yet. So that's, yes, this is the question, yeah. So normally, everything in neural networks has a fixed size. So if we want to multiply this matrix by something, well, if we're multiplying by something along the column axis, we're in trouble because we need to have a different matrix for every size. So it seems like a big problem. So let's, so first, that's what the matrix looks like. So we're going to come back to that. That's the interesting question. Anyway, here we are in 2017. There are lots of ways to construct F. Basically, people have their favorites. They tend to push harder on the ones they like, and there aren't really very many systematic comparisons of them. If you're the sort of person who likes being very systematic about comparing things, I think this would be an interesting thing to to look at. There's also a new, very exciting kind of way of constructing the matrix where you define a function you define each column as a function of the word that it is that's currently being represented and the rest of the sentence. And you've got to deal with sort of adaptively large things. But this is really nice because you can compute the representation of all the words in parallel, and you don't have to run. So there's some people don't generally like RNNs for production use cases because if something is, you can't use parallelism to reason about the representation of the entire sentence. You have to read it from left to right and from right to left, and you can't parallelize across time. And if you're trying to, say, serve up a translation in 50 milliseconds, that's painful. And so there's this very nice paper called All You Need Is Attention from Google Brain that comes up with a way to do all of this in parallel. That's the one I left out. Anyway, that's where we are today. With representing these matrices F. But now let's assume you've decided what your representation F is, and we now are going to decode. And as we just had a question about, like, how are we going to deal with this? F is going to be different in sizes. Aren't we going to need a whole bunch of different matrices to deal with this? Yes, you would think so, but there's a clever solution for generating from matrices that lets us sidestep this issue. So here's the high-level idea. We're going to generate the output sentence word by word using an RNN language model, just like we've always done. And at every output position t, we're going to receive 2 inputs rather than just 1. We're going to in addition to any recurrent inputs like the cell or the hidden state or things like that. We're going to get a fixed size embedding of the previously generated output symbol. So here I'm calling this E1 in translation we often translate from F, French, into E, English, in homage to the original work in machine translation that was done between French and English. So that's the standard sort of recurrent, or the sampled connection that we have in RNNs. And the second thing we're going to do is have a fixed size vector encoding a view of the input matrix. So we've got to now decide how, at every time step, to select some part of that input matrix that's appropriate for the next thing. So how do we get a fixed size vector from a matrix such that that fixed size vector kind of encodes the upcoming information that we want to be able to predict next in a sort of sensible way? And how do we do this without having to have a whole bunch of different matrices of different sizes? So the approach proposed by Dmitry Badenow, who was interning in Montreal at the time, was to do a weighted sum of the columns of F based on how important they are at the current time step. And so if you think what a weighted sum of columns in a matrix are, if we've got a weighting vector, so it's going to be length n, where n is the, say, length of the number of columns. And we've got this matrix F, that's just the matrix vector product FA. So we need to be able to come up with this vector A at every time step. And that vector has to be of different lengths depending on the number of columns in F. So the weighting of the input columns at each time step is called attention. Okay, so basically, schematically, this is how things work. So if we recall RNNs, we basically generate sentences, we get our start symbol, we feed things in, we feed in the thing we've just sampled, and together with the recurrent connection, and we sample things. Now we're going to have this auxiliary matrix, and what we're going to be doing is we're going to be deciding, we're going to aggregate this matrix in some way into a vector. We're going to attend to it, and we're going to use this to feed in the, we're going to use this to determine the inputs now to these recurrent states. So the initial state is going to be some function of this matrix. And we're now going to be computing this attention vector at every time step. And I'll say how we compute that in just a second. But first, I just want you to understand what we do with this. So at time step 1, we're going to say, and I'm showing basically the darkness of the circle is going to indicate how strongly we're attending to each position, each column in the input matrix. And so just the idea here is each word, say, has its own column in the matrix. So each attention vector is going to be just as long as the number of columns. So at time step 1, let's say we want to strongly attend to the first column of the matrix. So we're going to compute now a vector called C1, the context at time 1, which is just going to be this static matrix F times A1. And that's going to be reweighting all of those columns. And those things together, we're going to now have two vectors feeding into the RNN state as input along with the recurrent connection. And then together, those two things we're going to use to compute the updated hidden state. We use that to sample the first word of the translation. Now we're going to go to the second word. We're going to feed in the thing we've just sampled. We're also going to compute a new attention vector, and we're going to use the previous state to make the decision about what to attend to. We're going to compute A2. We're going to now compute C2 just by multiplying F by this vector we've just computed and feed that in. Now we've got the two inputs at time step 2 to the RNN, and we can repeat this process. And we just basically keep doing this until we get to the end. And one of the interesting things about this is at the end of the translation, you can actually visualize the attention, and you can see where the model was looking when it was making decisions about what word to generate. And that's often a good way to. Neural nets are often considered to be very uninterpretable, and attention is appealing because it actually has lets you see a little bit more what its mental states are. Okay, so the big question is, how do we know what to build, what to attend to at each time step? So how do we compute this A sub t? So at each time step, so that's one time step is one output word, we want to be able to attend to different words, different columns of that input matrix. So we need a weight for every column that is an F-length vector AT. So here's a sort of simple solution. So we're using this RNN to predict the output model. And let's call the hidden states S sub t. And S sub t, of course, has some fixed dimensionality because it's just a standard RNN. We'll call it M. And at time t, what we're going to do is we're going to compute. So we want to generate the tth word. And so we haven't yet computed S sub t because it's going to depend on the thing we're attending to. So we're going to use the most recent information from the RNN, namely S sub t minus 1. And we're going to compute some function. And we're going to call this we're going to compute a representation called a query key embedding. So basically, it's just going to be a transformation of the previous hidden state in the output RNN. So S sub t minus 1, let's just multiply it by some matrix V, and that's going to be a learned parameter. And if we take the dot product of the query key, this RT, with every column in the input matrix, we're going to get a scalar for each of these. So we've got the query key, we've got every column, which is a vector of a known size, say that also needs to be the size of the query key. We're going to get a score. And we do this now for every column in this matrix. So it doesn't matter how many columns there are, we're just doing the same operation with the same query key over and over again. And so basically we're building this vector, let's call it UT, which is going to be, it's going to have the number of rows equal to the number of columns in that input matrix. And now we're going to exponentiate and normalize using a softmax function. We'll call this A sub t. And this just guarantees that our attention weights are going to be between 0 and 1 and sum to 1. So it looks a bit like a probability distribution, but we're not actually going to do anything probabilistic. We're not going to sample anything. There's going to be no hard decision about where to attend. We're just sort of saying, I think I should look mostly over here and maybe a little bit over here, and we're going to then take this weighting and use that. So finally, we're going to compute this context vector at time t just by reweighting the columns of f with the thing that we've just computed. So this lets us sidestep the concern about needing to have different sized matrices to deal with this vector. We don't have to worry about having different sizes because we're going to programmatically generate this vector, which is going to have a variable number of elements, or it's going to be dependent on the size of f, so we don't have to have like parameters that are learned, because we're, in some sense, computing the parameters on the fly. Okay, so this inner product model, sometimes called multiplicative attention, I think, or additive attention, something. It's not actually, this inner product attention isn't actually used terribly often. It turns out it's better to do the following. So basically, you add together the query key and each column of the matrix, and then pass that through a nonlinearity, and then multiply that by a learned vector to compute the scalar. One thing I'll note is here, W and V are learned parameters. And this addition, so here you've got this matrix-matrix product, and you're adding a vector to it. We're going to add by each column, so we're broadcasting over the columns in W and F. And this is going to learn some more complex interactions. And in practice, this model, this Badenow additive attention model, works a little bit better, although I think it varies a little bit. So I think you should always try the simpler one. Okay, so this has been, there's kind of a lot. So let me show you what this looks like a little bit in pseudocode. In fact, if you implement this in something like Dynet, it looks kind of like this in real code. So basically there are two parts of this. So we're going to first start out by encoding the sentence as a matrix. So that was part one of this part of the lecture. We're then going to start excuse me. We're then going to start by initializing E0 with the start of sentence symbol. And we're going to we're going to define S0 either as a learned initial state or Badenau used a function of the right to left LSTM as kind of how to define the initial state of the output LSTM. In practice, it doesn't make a huge difference here. We're then going to initialize t equals 0, and then we've got this loop. And we're just going to go through here, and we're going to sample the next word according to the rules we've just talked about. So the first thing we're going to do is we're going to increment t. So on the first iteration, t is now going to be equal to 1. We're now going to compute this query key, r sub t, so r sub 1, and that's going to be a function of the current, or the previous hidden state, S sub 0 in this case. So S sub 0 is already defined, so we're all good. And we are going to then compute the attention energy. So we're going to compute this UT, which is going to have the same number of columns or same number of rows as F has columns. And using this Badenau formulation or the inner product attention formulation. And then we're going to normalize this vector over, however many rows it has, using softmax. So that these last three steps, this was just the second part of, how we compute attention. Now, we're going to compute our fixed dimensional encoding of our summary of the matrix that's appropriate at this time step just by multiplying F times AT. And now, we're going to compute the new hidden state of this output RNN. We're going to feed in the previous state, and we're also going to feed in this concatenation of an embedding of the previous time steps output word and this summary of the input matrix that's appropriate for this time step. And then we project out to our softmax, to our vocabulary, and we get a probability distribution over the next word, and then we're going to sample the next word. And then we're just going to repeat this process until we get to the end of the sentence. So it's super simple. So a couple of things. I promise. It's if you had seen old machine translation systems, you'd be like, oh yeah, it's simple. The world really is getting better. So at training time, again, we're not going to sample ourselves. We're going to rely on the universe to sample from us. We're going to sample for us. We're going to take some parallel data and say, these are the translations that exist out there. How do we fit them? And we're going to replace that sampling step with computing of the log probability of the things that we're actually observing. And everything proceeds as normal. During decoding time, we can either do the sampling or we can do a beam search. Okay, so a couple of things to note. When you write code like this, you want to do your best to factorize this so that computations that are expensive, that can be factored out of an inner loop, get factored out. So this product W times F, that doesn't change as during any iteration of this loop. So we can replace this with a variable x and just save a little bit of time to doing this. So, all right, so if we do attention and machine translation over the standard sequence to sequence model, you get 11 blue points, which is one of the probably hugest improvements of any paper that had ever been written in machine translation. This got a huge amount of attention at the time. It's now what to overuse a word. It now is what powers, if you use Google Translate, at least in most languages, neural machine translation is based on this model is what's running behind the scenes. As I said before, you can look at the attention patterns and you can see actually the things that the model is attending to when it translates certain words look sort of intuitively plausible. If you look at these things and see patterns that look bad, it's an indication that maybe your learning is suffering. Maybe you don't have enough hidden dimensions. Maybe you have too many hidden dimensions. So this is another way of looking and kind of trying to understand how well the model is working. So why does attention work as well as it does? So I think one of the big helpful things is gradients have a much easier time when they're during learning, of getting to where they belong. So imagine we have, we're predicting the word beer here. This is, I'd like a beer is the translation we see in our reference data. So let's think about what's going on when we are back propagating. So say beer was predicted with low probability and we need to update it to make the probability more likely. We are going to propagate. So the first thing we're going to do here is we're going to weight the columns of this matrix by the current values of the attention. And so we're going to get something that looks like this. So most of the attention is focused on the single word beer. And so when we when we do backpropagation of errors from the incorrect prediction of beer, a standard learner that doesn't have the benefit of attention is going to have to backpropagate, say, all the way back through this and get back to, say, go through that vector bottleneck to make a change to, say the embedding of the source language word beer is the problem, and it needs to be updated. It's going to have a long way to travel. Whereas in this case, we're going to have this direct connection that's going to let a gradient flow immediately back into here and update this word embedding in a fairly direct way. And so one thing to notice is, the attention is going to fan out the error across all elements of the input in parallel, but it's going to be weighted by the thing that you're attending to. So if your attention model is learning to point to sensible places, you're going to be able to update the words in a much more efficient way. So assuming your attention model is learning, but since you're learning both of them together, obviously, these things can fail. But in practice, we find attention seems to converge fairly quickly, and we then get very good performance for this. So this is, basically some intuition for why attention is helpful. So tonight's speaker, Kyung-Young Cho, when I saw him present this work, because he was on the paper that had proposed this stuff, he had asked whether a translator reads and memorizes the input sentence or document and then generates the output sort of from memory. And you can kind of think about the original sequence-to-sequence model as doing this. And he said that, common sense and experience say that, translators don't memorize the whole input sentence and then try and produce it again. They're constantly referring back to the input when they're doing their job. And this has actually been backed up by, eye tracking studies. And I think this is one thing, just as, you go out into the field and work on machine learning, there's this question that often comes up, which is, to what extent should humans be models for machines? And I think, here we've seen a real success. We're taking some inspiration from human behavior, led to this very interesting model. Of course, we can point to things like airplanes and say, well, they work differently than birds. So, you can kind of find both answers. Okay. So we've got here, attention is a very, very important thing. I focused on translation as a representative example. It's used in things like question answering. It's used in various information retrieval tasks. It's even now being used in monolingual language modeling, so unconditional language modeling. And there's still a bunch of work being done to improve how attention works. So there's something a little bit strange about it where attention seems to just care about the content. There's no bias in favor of particular word orders or like not attending to the same thing over and over again. Sort of the data has to determine everything about the attention. But often we know things about sort of where information is likely to be encoded in the sentence and, or whatever we're attending to, and maybe we'd like to build that in. And there's a bunch of ongoing work. And finally, attention weights provide interpretations you can look at. Okay, so we've got about 5 minutes left, and we can either do image caption generation with attention, or I can talk about some kind of tips and tricks for working with RNNs. And I guess I want a show of hands I can't do both. So I want a show of hands for who wants to talk about image caption generation with attention. And, okay, put your hands up. Okay. And who wants to talk about sort of tips and tricks for working? Okay, all right, we'll do that. Image caption generation is really cool, but evidently not as cool as some of the tricks of the trade. Okay, so there are a few things you can do when you're working with RNNs. So I'm going to talk about depth, dropout, and also a variant called recurrent dropout and mini batching. Okay, so we all talk about doing deep learning. What does that really mean? Well, nobody really means. So to a certain extent, you can think about the representation of the input when you get to sort of the end of time. There's been a lot of stuff that's happened in between that's very deep. But that's not what we mean with deep in LSTMs. The standard thing we do is we stack them on top of each other. And we keep doing this. And so rather than having just one layer of nonlinearities, we tend to have multiple layers of nonlinearities. And this lets us learn more non-trivial transformations of the input and interactions between the current representations of the memory and sort of how things evolve over time. And so this is usually what we mean with deep LSTMs. Oh yeah, and then we maybe do one prediction. So this is all, there's nothing complicated about this at all. We just take the hidden state here at time t, and we feed it in as the input at the one layer above. And so this is very easy to implement. One of the other things that is often done, especially as things get very deep, is to add what are sometimes called skip connections or residual connections. So the idea is, we never want to forget our inputs. The inputs are really what we're modeling, but we want to get sort of more and more abstract representations of the input. And to make it a little bit easier to get the gradients to flow all the way back to the beginning, we have sort of two paths that connect. One that goes through the nonlinear transformations, and the other that does a direct connection. And you can either concatenate these, or you can add them together. So does depth matter? It kind of depends. It usually helps. I'll say it depends a lot on what the signal is that you're modeling. So in text, it's often less important to have very deep models than it is for audio and visual processing, where it does seem to have a bigger impact. I think we had swung the direction of saying that depth matters more in text. And now the pendulum is swinging back, and people are going with shallower architectures. Basically, if you tune these things, it doesn't matter. It seems like the most important thing is the number of parameters in your model, not sort of whether they're sort of spread out along deeper architectures or shallower ones. So I think that's kind of the current received wisdom. Again, this is an open area of research, and this is a very empirical question because we don't really have theory that lets us analyze this too well. There's some, but not a tremendous amount. So basically, I'd say use 2 to 8 layers Probably 4 is like the most common for kind of big problems. These input or skip connections are used often, but not universally. They often become necessary if you want to get these models to work when you get to very deep architectures. So dropout. Dropout is a standard strategy used to improve the robustness of neural networks. It's a kind of regularizer that prevents neural networks from sort of explaining the inputs in a too fragile way. So often it'll become very confident in one particular prediction. The idea behind dropout is at every time step, you randomly knock out certain components of your hidden activations. And so some information that is usually there in predictive is just no longer available. And what dropout does is it encourages information to be distributed and redundant. So the network has to encode some copies of the same information. This turns out to be really useful. But if you drop out across time, eventually, with very high probability, you're going to have forgotten everything from the past. And since we want to use memory, this is not good. So what we usually do is we just apply dropout between the layers, but not on the recurrent connections. However, we can use what's called recurrent dropout across time, but the trick is you have to use the same dropout mask at every time step. And the reason for this is, of course, that you're then basically, certain memory cells are just going to not be available. They're not going to be reliable. But we're not going to, with high probability, eventually have forgotten everything. It's going to be the same. On each iteration, we're going to have a different set of cells that are on or off. But we're not going to sort of progressively forget more and more. And this turns out to be very, very useful. OK, for implementation details, you can use diagonal matrices instead of full matrices, especially for the gates. It hurts a little bit, but it makes things a lot faster. You can concatenate parameter matrices for all the gates. You can compute all of them actually in one and do a single matrix vector or matrix-matrix multiplication. There's some very nice new optimized implementations from NVIDIA. And you can use GRUs and reduced gate variants of LSTMs. Another trick that's very useful is to initialize so that the bias on the forget gate is large. So intuitively, at the beginning of learning, you're just putting random stuff into memory. So it's not worth keeping your random memories around. So you just want to forget often. And then the model will learn to start using it when the memory contains something interesting. If you are putting a lot of random stuff in memory early on, you can run the risk of learning kind of random correlations, which is bad. And then also use random orthogonal matrices to initialize the square matrices. OK, so I think we're just about out of time. You can do mini batching. Graham covered this yesterday. So I'm going to skip over this and just ask so you guys can get to lunch if there are any questions. Yeah. You don't need to do any pre-training of the language model. You actually, or pre-training of the source model or target model. You're going to, yes, but you're going to still just read the words, but there's going to be no predictions that you make when you're encoding the source. So at every time step in the output, we're going to have this generation of the next word of the output. But while we're reading the part of the model that reads the input, there are going to be no predictions that are made at every time step. So that's a good question. And you could think about adding like an auxiliary loss, like can we teach the model to predict the next word? And people have looked at that, and it doesn't seem to help. But yeah, the idea is we just have two LSTMs next to each other. The first one doesn't produce any output. Yes. Yes, that's right.
And that, you know that since for example, the information for the whole French vocabularies are too big to be placed in just a vector, they're going to produce a matrix and then use the attention mechanism to just filter a color from that matrix
For each time step. That's right. That's right. Exactly. Yeah. All right. Any other last questions? I'll be around for a few minutes up here. Okay. Yeah. Yeah.